My name is Yujian, and I'll be presenting the first talk tonight. And our first talk is about vector databases beyond RAG. So many of you who have heard of RAG have probably heard of vector databases. And I don't know why I didn't ask that question earlier, but who has heard of vector databases? Oh, great. Okay, cool. So you guys, a lot of you guys know what vector databases are. Okay, so I'll give you a quick introduction to Zilliz, and then a quick introduction to me, and then a quick introduction to what we're going to talk about, and then we're going to get into the meat of what we're going to talk about. So Zilliz was founded in 2017. Our CEO slash founder was an Oracle guy. We are currently located in Redwood Shores. We raised 113 million around in our Series B, and I think this is actually wrong. There's more than 113 employees now, and we have 1,800 plus. Actually, I think this is also wrong. It's a little bit less than the number of enterprise. So that's a little bit about Zilliz, and then a little bit about me. That QR code links to my LinkedIn. If you want to connect with me, feel free to scan that, send me a connection request, be like, oh, we met at Unstructured Data Meetup. I am a developer advocate at Zilliz, and a little bit about my background. So as I alluded to earlier, I've been working in AI ML for a while now, since about 2014, 2015. I studied computer science. I published some papers, machine learning. I worked on the auto ML system at Amazon. I started working in startups. So that's kind of a little bit about my history, my background.
I just checked the weather.
I'm going to advertise this again. This is not the right QR code.
It's going to be like snowing by like 10 times.
Okay, so this is what we're going to cover in our talk.
See, your flight arrives when? He's like,
we're talking about why vector databases. What are these things?
Why go home, my breath. How about that?
And then we're going to talk about how do vector databases work. So what's going on underneath the surface? What are the underlying functionalities that you know about? And then we're going to talk about some use cases. So I'm going to show you some ways you can use vector databases.
A wind stream.
And then if we have time, we'll also get to cover more of the architecture, or we might just very quickly cover it in some. So first of all, why vector databases? My timer out.
From the routine, then there's like a hit.
What's that noise?
His last time.
I turned down the gain, and that kind of took care of most of it. But
I'll just drive camera back in here and be like,
where's that coming from? No.
Hey, bud.
Where's this coming? Okay, wow, that's really weird. Okay, so why vector databases? They allow you to compare data that you couldn't compare before. And the reason they allow you to do that is because of the way of the type of data they work with. Okay, so vector databases are designed to work with this type of data called unstructured data. And if you have been not living under a rock for the past 10 years, you've probably heard of this term unstructured data. And you might have even seen this little snippet that says 80% of our data is unstructured data. The point behind this slide is basically to tell you that unstructured data makes up more data than structured data, which means we have opened the door to working with more data than we currently have ever been able to work with. So that's kind of what unstructured data is, and that is what vector databases are meant to work with. And the way that we get vectors is that we take this unstructured data, which could be images, it could be text, it could be audio, it could be video, and we run it through a machine learning model. We run it through some sort of deep learning model. And then what we do is we cut off the last layer of the model, and we just take the outputs from the second to the last layer. Now, the reason we do that is because the last layer of the model is the predictive layer, where the model is going to give you some sort of prediction of what it thinks of your data. And so because what we want is we want a representation of that data, we want a numerical representation of data so that we can work with it, we take the output of the second to last layer. And the reason we use the second to last layer and not any of the other layers is because as you push data, as you run data through a neural network, every layer of the network picks up some sort of new semantic meaning of that data. And so the second to last layer contains all of this meaning. So that's why we take the output from the second to last layer. And that is basically where you get vectors, and then you store them in a vector database like Zilliz or the Zilliz project. Okay, so I'm going to just cover some examples of unstructured data so we understand why unstructured data is hard to work with, right? So let's look at these 3 sentences that I have here on the screen. How does your company increase its bottom line? How does your company make more profit? And how does your company increase profitability? All 3 of these things mean the same thing, but if you were to do traditional search, you would not be able to find these 3 things in one search. You would have to do multiple searches because the words bottom line, profit, and profitability are not the same. Despite the fact they actually mean the same thing, they're semantically basically the same. They're semantically similar. They're not the actual same token, so you'd have to do multiple searches to find these. Okay.
Thank you much.
Next example. This is one of my favorite examples. Who knows who this is on the screen, by the way? Raise your hand. Okay, Joan, you can say this answer. Who is this?
Come on in.
All right, first stock. Oh,
Your event's going to be in the room to the left here.
So the point of this is actually to show you
sound.
that vector databases do something that is something that we have to do all the time. So one of these pictures is not Taylor Swift. And I'm going to ask you all to raise your hand for the picture that you think is not Taylor Swift, okay? Raise your hand if you think the first picture is not Taylor Swift. Okay, raise your hand if you think the second picture is not Taylor Swift. Okay, what about the third one? Okay, what about the fourth one? Oh, wow. Okay, so everybody thinks the first one is Taylor Swift, though. Wow, okay. I guess that was just a very iconic look. Okay, the second one is the one that's not Taylor Swift. So I just wanted you to kind of go through that exercise of being a vector database. Okay, now you've been a vector database. You've done what a vector database does. It says how similar are these pictures, which one is the least similar, or which one is the most similar, etc. Okay, so that's text data, what we just looked at here. Image data is what we just looked at here. So basically, the idea is that you turn all these things into pictures. You use math to quantify relationships between these entities.
I do not badmouth her anymore because I know
how do vector databases work?
Wildly into it.
Vector databases efficiently store, index, and relate entities by quantitative value. We use vectors and we compare to see how close they are. And vector similarity, which is what we're going to talk about next, we're going to talk about similarity metrics. Vector similarity is a mathematical measure how close 2 vectors are. Okay, so let's look at this slide. This slide is an example of semantic similarity. And basically, what I want you to take away from the slide is that you can do math on things that were not originally numbers, in this case text, by using vector embedding.
Doing a series with Frank, we called it with AI
so I want to also point out a couple things. That you will never see 2 vectors in production.
He
and you will never use Manhattan distance, which is the distance that I'm about to talk about in production. At least
it's
very
just
rare.
Imitation.
And we'll talk about what's actually used
it's not how we
in a couple of slides. For this one,
which is helpful, but
semantic similarity, we have these 4 words: queen, king, woman, and man. And I want you to notice a few things here. So number 1 is that the first dimension of the words queen and woman are the same. But that doesn't necessarily tell us what this dimension means. It doesn't mean that this is a dimension that specifies gender or sex or whatever. It's just that along this dimension, these words mean the same thing. They relate along the same way in this dimension.
Visibility.
Okay, so let's go through some quick math. I'm going to go to the other side for this. Queen is 0.3, 0.9, right? And then woman is 0.3, 0.4. And so when we subtract these words, we get 0, 0.5. Who wants to take a guess at what this word might mean? What might this little 0, 0.5 vector mean? Yes. Okay. So that's
Newman, Julia,
Okay. Great. So I'm clearly not asking the question that is going to give me the answer that I want. Let's say, what's the difference between the words woman and queen? What might be that difference? What is that semantic difference? Yes. I'm sorry? Okay. I'm just going to say this might mean something like royalty. And then we add this to the word man, and we get 0.5 on the first dimension. So we get this on king, and then we get 0.5 plus 0.2, we get 0.7, which is king along these two dimensions, okay? I'm not saying that 0, 0.5 necessarily does mean royalty. I was just trying to get people to guess at what the difference between these words might mean. Okay, so similarity metrics, the way that you measure how similar two vectors are, is a way to measure distance in vector space. And here we're going to cover three similarity metrics, and we're going to start with the first one. This is L2 or Euclidean. So this one is basically x squared minus y squared, or x1 squared minus x2 squared, and you just get the distance between 2 points in space. Now this formula looks a lot like another formula. Who here knows what right triangles are? I should see everybody's hand go up for this. Nobody knows. You guys don't know what right triangles are? Come on, guys. Okay, so you guys remember what hypotenuses are? Right? Everybody knows.
Revolutionizing education with AI.
That's essentially what you're measuring with this L2.
My grandma called me today and let me know that AI was going to take up to 60% of everybody's jobs.
Yeah, another distance measure would be inner product.
And what jobs exactly?
So inner product is dot product, a little more advanced than triangles, a little more advanced than rectangles. If you remember, I don't know if this is trig or linear algebra, but at some point you probably took some sort of matrix math class and you saw this thing called dot product, and that is what inner product is. And what this measures is the projection of one vector onto another. So it measures not just the orientation difference, how the vectors point in space, but also how far apart they are in space physically. So this measures the projection and gives you one number that measures both of those. Okay, and then the third vector similarity metric we're going to talk about is cosine. And cosine is measures essentially the orientation difference of the vectors. How far apart are they pointing in space? So these three vector metrics are all different ways to measure how far apart the meaning behind your vectors are. And Euclidean, or L2, measures spatial distance. How far apart are these words semantically most likely you would probably use this in a non-normalized vector space. Cosine is orientational distance. How far apart is the meaning pointing of these vectors, right? So maybe the biggest cosine distance you might be able to find in like a two-dimensional space might be like big and small. And then inner product is both. It measures both how far apart is the orientation, how far apart is the meaning pointing, and how far apart is are the meanings in space. And then I just want to point out with normalized vectors, inner product is equivalent to cosine, right? So right here's cosine, a dot b divided by the magnitude of a times the magnitude of b. Let me go point at it on the screen. A dot b, magnitude of a, magnitude of b. And then inner product, which is just a dot b. So here's a quick question. I don't know if anybody's going to know the answer to this one. Which one do you think takes less compute power? Any guesses? Any other guesses? All right, we're going to move on. It's IP, by the way. I just want to point this out. Cosine, right? A dot b divided by the magnitude divided by the magnitude. You got to do about, let's see, 1, 2, 3, 4, 5, 6, 7, 8 calculations there, I think. This one, you just got to do 1. Okay, moving on. Indexes are the ways that we organize the way we access our data. So now we're going to talk about how to actually retrieve and once we get to a certain scale. Yes.
To the bathroom, to the TV, to the kitchen.
What is a normalized vector? Yes, a normalized vector is a vector with a magnitude of 1. That means it's x2, x3. By the way, here's a sock. You want to catch it?
I bet it's intimidating.
You have x1, x2, x3.
Especially after
x1
being
squared plus x2 squared plus x3 squared is 1.
Traumatized.
That's what a normalized vector is.
True.
Okay, so let's look at some indexes. Indexes are the ways that we organize the data so we can more easily access it, which is not very important when you only have like a couple data points, but it's just very important when you have millions of data points, or even when you have thousands of data points. So the first index we're going to look at is inverted file index. Inverted file index is probably the most
however, it is a Tuesday about
indexing
15
method
people
that I can think of by itself. And essentially what you're doing here is you're doing a k nearest neighbors, you're doing a k means
15 people. I can order them
Domino's. Right. So think back to your intro to machine learning class, taken one. If not, think back to what I'm about to say in the next 5 seconds. There's a algorithm called k-means in which you tell it, hey, there's k clusters, and I want you to cluster this data in such a way that these clusters are all organizing similar amounts of data, basically. And so that's one way to index your data. And essentially what this does is this allows you to just keep the cluster centroids in memory. And then when you do your search, you only need to search the cluster centroids initially, and then you dive down and search the actual vectors. And so this saves you a lot of memory. And the performance on IVF is pretty good. And then the next index is HNSW, or Hierarchical Navigable Small Worlds, which is and this is a graph-based index. So what this does is when you put your data points into this index, it creates a graph. And what it does is it creates a graph where it points to, it has like
oh my gosh, I'm working today. Literally both.
And then as you insert it, it also assigns a uniform random variable. Uniform random variable, it will be put into another layer. Let's say maybe your cutoff is 0.9. In that case, things that get assigned 0 to 0.9 are, or everything gets into layer 0. And then things that get assigned above 0.9, so from 0.9 to 1, they get put into layer 1. And then things get assigned 0.99 to 1, they get put into layer 2. And then 0.999 and so on get put into higher layers. And then at search time, you start at the first layer, so you start at the most sparse layer, and you find the closest neighbor, and then you go down and down and down and down and down. Now, the really nice thing about this is that because you're holding all these lengths in memory, all of these distances in memory, you have a very, very fast index. And you also have a very, very accurate index because you get access to everything. The downside for this is that you have to, this is an index that takes up a lot of memory. So you have to have enough memory to hold this index in memory. Okay, so how do we solve those memory problems, right? There's this method called quantization. And Milvus offers 2 types of quantization. The first one is scalar quantization. And essentially what you can think of with this is, let's say you have all of the numbers, all of the real numbers from 0 to 10. And those numbers are the numbers that the values of your vectors could be, basically. And in order to make this easier to work with, what you can do is you can bucket those numbers. So instead of saying 0.23197, you can say this is close enough to 0. And everything from 0 to 0.5 is 0. And everything from 0.5 to 1.5 is 1, and so on and so on. So that's what scalar quantization is. It's a bucketing system. And as you can imagine, this limits the number of the amount of memory you have to store by quite a bit. Not only because of it makes it easier to deal with the actual numbers, but because of the data type, right? So now you're moving from float into int. And then product quantization is just the same thing except along 2 dimensions. Okay, so the overview for this, right? So IVF, intuitive, medium memory usage, doesn't take up a lot of memory, pretty performant. HNSW, graph-based, I wouldn't say very intuitive, high memory usage, very, very performant. Flat index, we didn't talk about this. This is just brute force. So memory, same. Performance, very, very performant, but also very, very accurate, very, very slow. SQ, bucketized scalar quantization, bucketized across 1 dimension, accuracy and memory trade-off, basically. This is your first accuracy memory trade-off. You get a little bit lower accuracy, quite a bit less memory. And then PQ, bucketized across 2 dimensions. This is more of an accuracy memory trade-off. Your accuracy gets worse, but your memory trade-off is a lot better, right? So from scalar quantization, I should have shown you this image for a longer time. From scalar quantization, what you essentially do is you can go from something like float 64 into like int 8. And so then you get an 8x. Oh man, 8 times. Yes, thank you. Yes, thank you. It reduces the amount of memory you have to store by 8 times. And then if you do that along 2 dimensions with product quantization, then you get 64 times, right? So, yep. So that's the way indexes work. And yep. So now we'll dive into use cases. So before we go into use cases, let's take a look at what vector data actually looks like. So here is an entry that I have in one of my vector database collections. And I want to point out the 2 most important pieces of this. Okay, so the 2 most important pieces are these 2 lines here, the ID and the embedding. So the ID here is made up, but you can also have an ID that is, what is it called? Auto-incremented for you. The embedding is something that you have to have. This is what vector databases are comparing. This is what vector search is on. It's these numbers, right? And you can see here, I'm using float since none of these are integers. And then the rest of the fields are what we call metadata fields. And metadata fields are things you use to filter on. So for example, if you, let's say I only want to find articles that have a reading time of less than 3 minutes, right? So reading time you can see is down here. Then what Milvus would do is it would produce a bit mask, compare the reading time, and only give you results with a reading time of less than 3. So that's essentially what the vector data looks like, and that's what the metadata fields are for. Okay, so this is the main use case. You guys have all heard of RAG. Everybody said they heard of RAG when I asked people to raise their hands earlier. And so what is RAG? RAG is basically when you inject your data on top of an LLM using a vector database. So what happens in RAG is you take your data, and is this on this side? No, it's on the other side. Okay. So you take your data and you inject it into Milvus, your vector database, and then you put this on top of the LLM. And at query time, the query goes and it goes to the LLM and says, "Oh, I want to know this," and the LLM structures that question into something that it wants to look for, and then it goes and says, "Milvus, okay, find me some similar things to this." And the Milvus says, "Okay, I looked through your data, and here are the most similar results." And then it goes to the LLM, and the LLM says, "Okay, let me take these results, make them human readable," and it comes back to you and it says, the primary use case for RAGs are factual recall, forced data injection, and cost optimization. If your question was, what is the primary use case for RAG, right? So that's RAG. This is the most, probably the most popular use case of the last year, at least for most hobbyists and enthusiasts. And other common AI use cases include recommender systems, right? So product recommendations, text/semantic search. Well, remember earlier I showed, or where we talked about the example of, what is your company's bottom line, profitability. Image search, right? We all looked at those pictures of Taylor Swift and struggled to identify which one was the fake Taylor Swift. Video, audio, molecular similarity search, all of these different things are things you can do with vector databases. And get out your phones. I have 3 QR codes for you to scan. And these 3 QR codes will lead to 3 different notebooks. And so here's our first notebook. This is a fashion comparison app that I made. And later on, we will be seeing a presentation about a much more in-depth fashion app made by someone else over here. And so this one allows you to compare a bunch of pictures, uses a segmentation model, segments out some clothes, compare some pictures. This is another example use case. Once again, we're doing image comparisons. This one is not fashion related. This one is done on paintings. And this notebook takes about 15 minutes to run, 12 of which is going to be ingesting your paintings. And then this one is one that is text-based. And what I've done here is I scraped the Wikipedia's entry for The Nightmare Before Christmas. And actually, I originally made this notebook for a Halloween presentation. And then I actually built multiple LLM RAG style apps on top of it. So these are 3 use cases that you can use and get started with, all in under like 15 minutes.
Cool, everyone can see this? This is going to be a quick talk on getting started with LLMOps, or kind of MLOps for large language models, and some ways to kind of, in general, build better AI applications. A quick background on me. I've worked a lot in computer vision, putting models on different devices like edge devices as well as clouds. And then I've worked in ML monitoring and LLM evaluation, and I'm working more on building ML pipelines and making MLOps easier for people. So during kind of my experience in this field, I've helped a lot of people on board with all these different things, and I'm kind of distilling some of that experience today. And currently I work at a company called Union. You can find us at union.ai. We maintain some really popular open source projects. One of them is called Flight and Pandera. If you've heard of those, Flight is used for ML orchestration tools. P-sign, I think you've heard of them. Which one? One or both? Awesome, cool. Ed. Maybe. Which Meetup? Oh, was I talking about ML monitoring? Probably. And then Pandera is also used for like testing your data or checking data quality on data sets. And we're hiring. So I think right now we have one role posted for a full stack engineer. So if you're interested, check that out on our site as well. And you can also connect with me on LinkedIn. So if you have questions about this or Union later, find me here or find me on LinkedIn. You can search for Sage Elliott. Hopefully I will show up. So Yujian already asked several of these questions. I'm not going to ask them all again, but I did like to, it's fun to kind of see people's experience so far. So maybe I will ask them. So who's used an LLM model? Probably a lot of people here, and you could count that as using ChatGPT, not downloading your own Hugging Face model. Most people probably. Who's used an API, like the OpenAI API? Makes it pretty easy to start building your own applications, probably. Who's messed around with prompt engineering? So you're trying to tell that model, like you take that API and you want to tell it to behave a certain way. Who's fine-tuned or trained a large language model? Still quite a few people. And what's really cool is you don't always need to do that right now with prompt engineering, depending on your application. Who has done or implemented some form of monitoring on your large language model when it's out? It's always fun because this is almost 0 people when I talk to them right now. And then, but you say you're doing prompt engineering, so you're probably adjusting a prompt or fine-tuning a model once it's out in production. How do you know that it's performing better when you changed your system prompt? What do you do right now? Do you just kind of look at it? Is it kind of a hunch? Someone want to actually tell me? Yeah, shoulder shrug. It's usually what I get. So we're going to talk a little bit about that. And who's deployed a large language model? So maybe you've trained them and you've deployed it. You've done like everything. It's exciting. I want to talk to you later. And then who's built some sort of, doesn't need to be a fancy thing, but like a CI/CD system. So you have a system available where you could get your new production data, fine tune your model, make it better, deploy it, use the ML monitoring to make sure it's actually performing better than your previous model. No. All right. Well, we're going to talk about how you can get started a little bit with this. And hopefully, even if you haven't done like any of these things and you're interested in doing it, and maybe I can break down that barrier where it might not be so hard. So what is LLMOps? So it's MLOps for LLMs. I kind of like to think of LLMOps as building AI together, but people are going to give you different definitions. And I use that because usually you're part of a team. You're not just one person, or you're tying tools together. So you're tying together some sort of system where you want to work with a team and other tools, and you want to be able to collaborate or enable collaboration and do that efficiently. And you want to integrate with all those other tools, like we've talked about what you should be doing, like in all these questions. Your MLOps system will probably have various layers of these. You want to do lifecycle management, model monitoring, like we talked about. How do you make sure that new model is performing better or the new prompts are performing better? And then you also want to be able to scale out like your compute as needed and reproduce deploying your model and people querying it. There's a lot of great graphics you can go check out. I kind of like to think of it as like a loop, though. Usually you're deploying a model, you've trained it, or you've done prompt engineering. Then you're collecting usually data from production, monitoring that model over time, and then retraining it and making it better over time, or catching errors quickly and then mitigating those risks. It also helps frame ML problems usually really well and reflects your business needs when you're communicating all these things going on with your ML system. So maybe it's their first time putting a model out. in your work environment, and when you did kind of the design with your coworkers, they might have told you what they were looking for, and then when you gave them those numbers, it wasn't exactly aligning with what their expectations were. So I kind of have a philosophy, which I actually get on another slide to help with that. So who should be using LLMOps? We saw a lot of people using like APIs here, but I kind of would say everyone, but to an extent. Like you don't need a incredibly robust thing all the time, but you'll probably want some sort of simplified version of a pipeline, which I'll show you today. Even for personal projects, this can help you kind of understand what's going on and quickly iterate on it if you want to make something really cool. But it's definitely going to vary a lot depending on your need. So you want to do things like resource management and scalability. That's going to help you deliver an experience to your users or to your personal project. And then you want to do model updating and improvements. That could just be prompt engineering if you're not actually fine-tuning a model. And then especially if you're putting on production and depends on the field, you want to be ethical and responsible with your model. Like if it's giving healthcare advice, how do you evaluate that it's actually giving the correct advice? That's a really hard problem, but hopefully you can catch those errors if it's giving anything that it shouldn't be doing, and then improve that very fast. And you just need a few tools to get started in the MLOps space. Look something like this. Just a couple. I think you can read all of these and make out all these logos probably. I'm just kidding, obviously, but this is kind of a survey of the MLOps space, and this was in 2021, I think. So I'm sure this is like tripled in size, if not way more. And if you zoom in, I don't think I can zoom in when I'm presenting, has these little chunks like this is infrastructure, analytics, machine learning, and artificial intelligence. There's monitoring here, there's open source. There's a ton of different tools that you can be looking at right now. But don't really get scared. We're going to simplify a pipeline for you. You don't need all of these things, especially when you're getting started. Here's another graphic that's kind of pared down a lot for LLMOps. It's hard to say a lot. This is from CD Insights. So they have some sections like your large language model developers, things you've probably seen before, like Google, Hugging Face, Meta, et cetera. These would be like where you're taking a model from. You have a data annotation. So if you are looking to retrain a model or fine tune a model and you're bringing in your own data, you probably want to use some tool to do annotation on, like Labelbox. You're going to provide annotations, pass that data into a model, retrain it or fine tune on it. Some other tools around curating data, vector databases. You can see Zilliz is in here. Good job. All the talks you've been doing have paid off. Your development platforms, tools around prompt engineering, large language model application development, deployment and serving, validation monitoring. I really like this piece, and you can see Y Labs is in here. I'm going to mention them a little bit later. And then security, which we're not really going to get into today, and then hardware optimization. And then I'd add one other piece, which is kind of the ML orchestration or CI/CD pipeline piece of things that's tying all these tools together. So you can bring all these tools in. Depending on your application, you may want something that ties them together, but it depends on exactly what you're doing. So here's kind of a more simplified example of a pipeline. You'd have your user input coming in, probably your system prompt telling the model how to behave. That then it's going to get kind of combined together, go to your model, and that's going to give some sort of output. And you might want to have a guardrail in place, which is just saying, if this model said something really toxic or bad, maybe you don't want to deliver that result to a person. And you'll see this a lot if you've messed around with GPT or anything, you ask it something, and then it says, as a large language model, like, I can't do that, ... That's some form of guardrail coming in. That can also be based on the user input. So, if you're asking it to do something illegal or tell you instructions about how to make a nuclear bomb or something, most of them won't do that. And that's a guardrail on the input here. So we're actually getting the input and the output. And what you might actually want to do is still pass that toxic input from the user to your model, even though you're not going to provide the results to the user at the end, but you might want to see how your model behaves. And you can store those prompts and responses in a data store. And then you can use those prompts and responses to monitor and see how your LLM is kind of either performing over time and how users are interacting with your large language model. We have RAG here. I forgot to draw arrows, but obviously you might use that to bring in extra data to your model as well. And then you have, again, some sort of tool that doesn't need to be a complex like orchestration tool, depending on your application, but you'll want something that kind of ties all these things together and that you can scale up if you want to like retrain a model on. So starting with LLMOps, when this field is changing all the time, so there's new tools popping up all the time. I'm going to show a few tools today really quickly, just like an example of what it looks like, what the code looks like. But the core ideas today are probably going to stay the same from what I've seen just working in ML and computer vision even before large language models were around. There's just some different ways around like evaluating large language models, but kind of the core things are probably going to stay the same. And my philosophy for at least getting started, again, it depends on your application and scale. Like one thing doesn't just fit every company here, but let's say a lot of people here like haven't deployed a model before, or haven't done ML monitoring before, and I would love for people to get started with that. So my philosophy for getting started, and you might want to do this again for like a smaller personal project even, is one, put a model out in production as fast as possible in some capacity. That doesn't mean that you're actually deciding like big business value results or big, you're not actually maybe providing the results to a customer. Like let's say you have an AI chatbot and you want to get it out on production data, but right now you currently have a team of humans writing responses like during a live chat system. But you could put a model out and have it kind of shadow deployed. So it's still getting the questions coming in from users on your system. It's providing responses. Those responses are actually just going to be stored for you to look at later. And then when you feel like, this model's actually better or just as good as like my live chat person, then you could ship that model out. But you're going to learn really quickly like what your model works well with if you put it in production in some capacity. Or if you don't have a full thing out, you might put this deployed somewhere and ask friends to go check it out, or go to a meetup like this and say, hey, everyone, I have this project I made. Can you all go to this link and ask it weird questions and so I can see how it behaves? And you'll probably learn a lot from that versus you trying to think of what people are going to say. People put in responses all over the place like you probably wouldn't think about before. And then you want to monitor that performance, and then you want to be able to have some sort of improvement process to take that data that you've learned from monitoring, again, maybe change your prompting, add guardrails, and maybe retrain a model. And again, you'll also learn a lot about how to maybe frame your ML problem, and if it's actually providing the right business value, if you can get this out really quickly. So maybe it's not the best model ever. Maybe you take a GPT model, do some prompt engineering, put it out, see how people are interacting with it, see what the results look like. And then from that, you might say, okay, I actually do want to take like a Hugging Face Llama 2 model. I want to fine tune it with data now and get different results. So I like shipping models, monitoring them, have some sort of an improvement process. So to get a model running in production, running on production data, again, if possible, or like I said, it could be kind of some fake production data like friends or Meetup people using it. Sounds like a no-brainer, but just like I mentioned, I think I just said this use case before, maybe your model's not even good enough. Should you put it in production? Yes, with a caveat. Again, it might not actually be, like if it was a self-driving car, you wouldn't actually want it driving the car, right? If you don't think the model's good enough. And you'll see that right now today, actually, in Seattle. I don't know if has anyone seen the Zoox cars driving around? Yeah, I see them all the time, at least in South Lake Union and downtown. But it's people driving the car, right? But they have the model running in those cars as they're driving around probably, so they can see how it's performing before they actually have it driving the car. So that's kind of a form of like, it's out in a production environment, they're seeing how it's behaving, and then they're collecting production data and they're retraining it. So you can do something like that with large language models. And what I'd recommend is, I think I just already said this. I got ahead of myself from the slides, but a tool shout out for this. So this is actually an image here of using Hugging Face Spaces. Has anyone used Hugging Face Spaces before? Few people. Has anyone heard of Hugging Face yet? Probably most people, right? They're really prominent in the NLP field. They do a lot of other stuff besides NLP, but they have a great setup where you can just take a model. You can also use their spaces, and they also have another app called Gradio, which makes it really easy to build a chat interface, or a lot of, not even just a chat interface, any interface around an ML model. And this is what it looks like. You can actually run this locally on your computer, but then if you wanted to quickly deploy it to spaces, you can. And it's actually not that many lines of code to kind of build this whole interface and have a model with it. You can see we just import Gradio, OpenAI, some of their libraries. And then this example is using a GPT 3.5, but it's actually really easy to also download a Hugging Face model like Llama 2, or I think Microsoft's newer one, the 2 billion parameter one, Phi 2 is on there now. You can download it, potentially fine tune it, and then quickly deploy it to an app like this. And you can even use something like Hugging Face Spaces. So if you thought deploying was going to be really hard, in production, you might want to use something like Azure, AWS, etc. But you can use Hugging Face. And I really like it for prototyping quickly. They also have a tier, and I don't work for them or anything, but they have a tier where I think it's like $9 a month and you get more inference time too. So it's really good for prototyping. You wouldn't use a $9 tier for production or anything like that, but it's good for kind of prototyping and getting quick feedback, because you can make the space public or have a shareable link. And then again, you could shout out a meetup or give it to your friends. Continuous monitoring and evaluation, the second thing I talked about. So LLMs are really tricky to measure. There isn't one silver bullet metric that you can choose to kind of look at them. There are a lot of kind of different complex metrics and simpler metrics that you can take and start looking at your model. Like Blue, BERT score, Rouge are some more complex ones that will give you some insight around like ML translation or how relevant is the response to a prompt using some fancy stuff. But you can also look at things like, what's the sentiment of your response from your model? Like, is it happy? Is it sad? Is it angry? If you're doing a customer service chatbot, maybe it shouldn't sound angry to customers. I've also found in monitoring, one time I was building an application where it was a customer service thing for like an online store. And I was pretending to be an angry customer. And I had a filter set up that was actually here in YLabs, which I'll give them a shout out here in a minute. But there is a filtering tool to automatically detect if like phone numbers or credit cards or any PII information was coming out of the model. And I was angry, and it gave me just a random fake phone number to call. Like I was like, hey, this product sucks. And it was like, oh yeah, call us here. And I was like, what? And I only found it because I had like a flag set up to tell me when something like that happened. Otherwise, I wouldn't have known, especially if you're doing this at scale. Like you're probably not going to read like hundreds or thousands or millions of messages, but you can have things like tell you when, some specific thing happened, like a phone number or credit card. Your LM probably shouldn't be giving out credit card numbers, right? In most cases, maybe there are some if you work for a bank. But I thought that was interesting. And so like you could fix that by then adjusting the prompt or having some hard-coded thing in there say, when you're providing a phone number, it should always be this phone number, not something you made up, which I thought was really funny. You can also look at things like people purposely trying to jailbreak your model. So you can calculate that based on embedding. So you can use something like a vector database and store known jailbreak attempts. And when a user gives you an input, it'll compare in there and say, this is pretty similar to other jailbreak attempts. So you're trying to get the model to do something that it shouldn't be doing. People do that by asking models in different languages or saying, hey, I made up this language, this is how you read it. And then they'll ask it to, give instructions again for making a bomb or something like that. And then it will often do that. Oh, also, you'll gain a lot of insight around how users are using your LM as well. So if you're tracking not just the responses from your model, but the input as well. And this is a little example here of using something called YLabs, which is a tool. They have an open source library as well called YLogs that you can start for monitoring LMs and doing a lot of this evaluation. They have a dashboard where you can easily set up monitors. And here's a little example of like this prompt is coming in. It's extracting metrics like sentiment score, jailbreak similarity, toxicity, et cetera. And then it's going to do that for the response as well. It also has a built-in metric that is kind of a response relevancy to the prompt, which is really cool. And then you can add custom metrics. So if there isn't any metric built in here that you want to use like Blue or Rouge, you can bring that in and build a custom metric. Again, I think I talked about these, but the tool, again, shout out to YLabs. There's other ones as well. And this is an example of the code. So again, if you thought it's going to be really, really complex to set up, it's actually not. This is not that many lines of code. And a lot of this is really just importing libraries and setting up an API key. And then you're going to log your prompts and responses, and you're going to get all that telemetry kind of that we talked about. So far, not too many lines of code here to build like an interface around your model. And if you were actually adding a Hugging Face model, not the GPT one, it's not that many more lines of code. And you can actually take this, deploy it to a Hugging Face space. And then again, not many lines of code for adding the evaluation piece. The other piece we talked about is kind of that CI/CD or continuous integration and delivery platform. There's a lot of other tools that you can use for this as well. This is an example of using Flight, one of the open source libraries I mentioned that we maintain. So this is kind of like a graph of what our workflow looks like. And this is the code. All really the extra piece of the code to use Flight is really just this top part here. We just add a task decorator, and then you can combine these tasks into workflows. And it here might be hard for you to see. You get some other things of saying like, how much resources do you want to use for this specific task? You can define that again, just kind of in that decorator there. So again, not much code that you would need to add this in. And Flight's a really robust ML orchestrator. So not much more code you would need to add in there. And this is going to allow you to really kind of iterate on all those things quickly. So we have that deployed model. We have the monitoring in place. We can now take new data in production when maybe also something like data drift occurs, where that means the new data going into our model no longer really reflects the training data. Maybe our model isn't performing as well. We can take that new data that we had from collection, kick off a training job, take that newly trained model, and then maybe we deploy it to production, but maybe we do something called a shadow deployment, again, where you have the older model running, you have this new model running now kind of in parallel to it, and then you can compare both of those models at the same time. And when the new model is performing better, hopefully, then you actually deploy that one into production. You can run across multi-clouds as well. So a lot of people I've talked to in the past don't always just use one ecosystem. So a lot of the clouds like AWS, Azure have all these really fantastic things in them, but people might be using certain features from one or the other. So it was pretty common a couple of years ago where people would do like training in BigQuery and then deploy on something like Azure and AWS. So shout out to flight.org there. Yeah. You'll want to kind of, yeah. There's a little bit more to think about it too. So Flight's also like typed where when you pass stuff out, like you have to be very specific about like, this is the data type coming in and this is the data type coming out. But it is really just a little bit of annotation around pre-existing functions. And then it kind of forces you to be really thoughtful about like types coming in and out. And that's like a feature. So again, going back to building AI together, yeah, I mean, it doesn't have to be strongly typed, and I'm sure there's other ML orchestrators that are not, but it's a big feature of if you're kind of on the ops side, like an AI engineer, DevOps engineer, depending on what you call it, the company that you're working for, and then you have a data scientist building something, they might not really care about the types coming in and out, and they're thinking this is fine, I'm just reproducing it in my notebook or laptop or whatever they're running on, but kind of actually making everyone in your company make things in a similar way or like the same way allows you to kind of take that and across teams they're going to be developing this the same, and then you can run those jobs everywhere. And you do a little bit of setup as well. So you have to install something called Flight Kit here, and then there's a little bit of setup that you can install locally with like that will manage your Docker containers, and as a Kubernetes backend, so it can scale up and down very easily. So where to start? Again, just reiterating what I said before, I would try to get a model in some form of production. I would say production, but in quotation marks sometimes. Use production data to see how it performs, even if it's not used in the final results going to customers. Continue to monitor and perform evaluation on that model, and then retrain models on the new data fast if you can, if you think that's going to improve your model, which often it does, but it does depend on your application. And then set up that kind of continuous loop. I don't think you'll regret it, especially if you're actually doing something with real users or customers. You're going to learn a lot by setting all that up, and you're going to be able to really quickly iterate and ship better models. So like if you're in consulting and you're bidding against people, which I've been in that situation before, and actually getting models like in production data and then showing that your model's better than the other person or can perform better can potentially be critical for your type of work. Choosing a tool. So really, I mean, work with what you know or just try some of them. Again, I shouted out a few that I like that I work with, but you saw that giant chart with a billion of them, right? So you could do a little research, see which ones work best for you. Some other tool shoutouts, just real quick, that you might want to check out. So for data, there's ZHub, which is a really cool local startup. I don't know if people have talked with them before. Oh yeah, and I see people taking pictures. Take a picture of this. Go check it out. And of course, I didn't fill in the ML orchestration part, which is where I work. But you can check out flight.org, I'd recommend, or union.ai. But yeah, ZetHub's really cool. DVC, obviously Milvus is the premier vector database. They have socks. Serving BentoML is really cool. If people haven't used them before, it's kind of a API tool. It feels a little bit like Fast API, but with really cool conventions for ML, and they have like versioning baked in. I don't know, has anyone used BentoML before? One person. For me, I'm like, oh, I feel like they're big, but I don't know how many people are regularly using them. YLabs, YLogs, Arise is another one you could check out. ML orchestration, like I mentioned, like Flight, Daxter. What's another one people know off the top of their head? Airflow, yeah, that's a huge one. Chaining, you probably heard like LangChain, Llama Index. A lot of people I know, LangChain just came out with a version something like 10 or 1 or like 0.10 or something like that. And I want to go check it out because I think it's supposed to be a little more stable. A lot of people I talked to in the last year like really liked it, but then they were doing so many changes and stuff like that, they'd get frustrated with it. And a lot of people I knew actually were switching over to Microsoft's semantic kernel, which might be something to check out. And then hosting, obviously, you probably all know Azure, AWS, GCP, and then Hugging Face is one that is really easy to get started with if you're kind of new. And then I would love to hear what tools you are enjoying. So talk to me after the next talk. I'll be hanging around. I will also have stickers to give away if you want any of those. So thank you, everyone. That's kind of my talk. You can connect with me on LinkedIn. Find our Flight GitHub, and we always appreciate a GitHub star, so you could do that as well. And if you want to talk to me on Slack, there's a Slack community that's pretty active right now. I'm also doing an AI book club every week right now in there. So every month we're reading an AI book. This month we're reading Designing ML Systems, which is really fun. And then I mentioned we're also hiring. So check out our site if you're interested in that job. And also, so did this seem interesting? I know it's like pretty quick in the talk format here, but would people be interested in doing like a hands-on workshop of actually all that stuff I talked about, walking you through it, and then maybe in like a couple hours, you could start from maybe never even training a model or using an API and then actually going through and kind of doing that whole stack that we talked about. See someone saying yes, people are saying thumbs up, awesome. So I'm gonna plan on probably doing that maybe next month or something like that. It might be virtual. Again, you can follow me on LinkedIn. That's probably where I'll post it. Otherwise, I'm not sure how to get it to everyone here. That's my talk, everyone. Thank you. And again, if you have questions, actually, yeah, because I'm definitely at time. If you have questions, just find me after the next talk, and then I would love to hang out with you there.
Amazing talk, Sage.
Hi, so my name is Joan, and today I will be presenting a personal project that I did. This is also my first time presenting, so I'm a little... Anyway, so a little bit about me. My name is Joan. I previously worked as a client advisor at Gucci, where I sold $1 million annually. One of my tasks during my job was to provide personalized outfit recommendations to every client, which serves as like an inspiration for my personal project here. So the content, the first part is going to just be the understanding the visual embeddings in general. So let's say you have an image here, and then it forms the channels, width, and height. So in general, there's like 3 channels, RGB. And then there's the width for this, for instance, it's like 6 pixels or 6 pixels. We pre-process it. In general, that would be normalizing the image to values between -1 and 1 or 0 and 1. And then we're also going to convert that to tensor. For the embedding model, I use a convolutional neural network model to obtain 512 dimensional embedding for each image. So this is how the architecture looks for during the serving stage of the project. So the user would request using a query item, so that would be an image, and there'll be an object detection models that detects fashion objects, and it will crop these objects into individual items. in order to obtain the vector embeddings of each detected object. And then we'll just run the similarity search through the vector index, and it will return the recommendations based on the detected fashion objects. So to simulate a catalog and build the vector index, so the images from the catalog, we'll just crop all the images in the data set and then obtain individual vector embeddings with an embedding model of all of these images and build the approximate nearest neighbors. The vector index, you can put other information that you need, but for the purpose of the project, I just put in the embeddings and the path to each image in order to return the recommendations. So the app demo, it's not showing up, I think. Oh, okay. Okay, so for this, I think the video is not showing up, so I'm just gonna do a live demo right here. Okay. Sorry, I'm just gonna run through something really quick here. Okay, so this is the page for it. So in general, you just browse the files and upload an image. I'll just go through. So I'm going to use a sample query right here. So this is just like the actual image. What it's going to do is it's going to detect the individual fashion objects in this image and then provide recommendations through that. So something like this. And then you can also refresh it to obtain different results if you don't like it. Okay. Sorry. Yes. So yeah, in general, so what I did was I put the results for each individual detected objects, like K at 5. So it just runs it randomly. So if, let's say, it detects one item, it will return the top 5 most similar items with, the L2 distance. And then it'll just return the 5 most similar items for that particular item. So if, let's say, it detects 5 items, then that would be like 5 times 5. So there would be like 25 different items in the recommendations. So every time you refresh it, that'll be different, but you can definitely adjust it. If, let's say, you want 10, then you would set the K at 10 in the code. Yeah, so you can definitely do that. For these project alone, since in the vector index, I only put the embeddings and the image paths, it doesn't have like a filtering ability, but we can definitely add that in, like if, let's say, with the object detection model, it doesn't send in the information for the product category itself. But it's something that you can add on to it. So you will just detect the object, and then it will identify what item it is, and then it will do the filtering category inside the vector index, if that makes sense. All right, does anybody else have any questions? Yes. So for that, so I trained the model. So I used a pre-trained YOLO V5 model from Ultralytics. And then I trained the model with the fashion data set. So, and then it will, so I already have a ground truth bounding boxes with the data set. I just retrained the pre-trained, I guess fine-tuned the pre-trained model, and then it will just give the bounding boxes information. Yeah. Does that answer your question? Okay, perfect. Sorry, I'll let you go first. Yes, so I use a public data set that is available on GitHub. The data set that I use is available publicly by Pinterest. I can connect with you and send you the link to the data set if you're interested. So for which one? So in the training data set, for this one, for the object detection model, I used 12,000 images in total. But in the actual data set, there is, I believe, over 100,000 images. Yeah. Okay. So yes, so first question, the vector database. I don't think it's actually like an actual vector database. It's like more like an open source index. It's called FACE or FICE. I'm not sure how it's pronounced, but it's by Facebook. So it's called Facebook AI Similarity Search, I believe, and it's open source on GitHub. And then your second question, what embedding model did I use to obtain the images? Was that the question? Yes, so what embedding model I used, right? So I used a PyTorch autoencoder model. Yeah, sorry. And does anybody else have any questions? How they create the embeddings? So I did not actually use the second to last layer in my case. I used an autoencoder model. So what that means is the model would try to copy the input to the output. And then there's a latent space in between in the middle. I can just show you the architecture really quick over here. Okay, so this is the architecture that I use like just for visual representation purposes. So the input is an image like this. So this usually we would convert the image to a tensor. And then we would resize it. In this case, I resized every single images to 128 times 128. So, you know, the total would be usually 3 times 128 times 128. So that would be the result for the input. And then it will just go down to this latent features. So this middle part is what I use for the vector embeddings. So you can usually kind of like, you know, adjust based on what you need. Most people just use a pre-trained model and just take the second to last layer. But in this case, I just use this latent features right here. And the reason for that is because usually for classification, you need the ground truth labels in order to train it. And usually it takes a real long time to manually label each image. For an autoencoder, you don't actually need the ground truth label. So it just tries to copy the input to the output, if that makes sense. Wait, sorry, what?
Where are you extracting the vector from in the model?
In the middle.
In the middle, right?
Yes. Okay.
And normally vector embeddings are not extracted from the middle. And so I think the question was whether or not you compared those and if you've seen any differences in when comparing them. So I did use a different, like, let's say classification layer before with Fast AI's model.
I don't noticeably notice any difference in terms of performance, I would say. If that answers your question. All right, is there any other questions? No? Okay. All right, thank you.
For that talk, Joan. Thank you guys all for coming.